Well, we're continuing on with more material from Chapter 5. And we concluded the prior video by talking about cases that were 1, 2, or 3 standard deviations above or below the mean. And we were working with the normal distribution and figuring out various percentages for those cases. Now, a score might be precisely 1 standard deviation above or below the mean, but on the other hand, a score, or we could say a value, could perhaps be 1.32 or perhaps 0.873 standard deviations above or below the mean. This brings us to a definition for a case's z-score, and that definition is the number of standard deviations that a case's score or value is above or below the mean. So that if, for instance, a case is 1.32 standard deviations above the mean, its z-score is 1.32. Or if a case is 0.873 standard deviations below the mean, its z-score is minus 0.873. So the z-score is telling us, and indeed is the same thing as the number of standard deviations that a case is above or below the mean. How does one compute a case's z-score, also known as a standard score? Here's the formula. Z-score equals the case's score or value minus the mean divided by the standard deviation. And the bottom half of this slide just is repeating some material conveyed from the prior slide. So for instance, if a score is 0.8 standard deviations below the mean, the z-score for that case, or for that score, we could say, is minus 0.80. And on the, switching the language around, if a z-score is minus 0.80, that conveys to us that that score is 0.80 standard deviations below the mean. Let's calculate a couple of z-scores. To calculate a z-score, we're going to need to know the score, the standard deviation, and additionally the mean. So we've administered a self-esteem scale. The mean for that scale is 25 points. We carry out the standard deviation formula from Chapter 4 and compute a standard deviation of 10 points. And finally, Anne's score is 17. What is Anne's z-score? Here's that calculation. X is 17. We subtract x bar. We divide by 10, that being the standard deviation, and the z-score computes to minus 0.80. 0.8 standard deviations below the mean. Let's calculate Rose's z-score on the self-esteem scale. Her score is 37. Here's the calculation of her z-score. X minus x bar divided by s, 37 minus 25 divided by 10. Her z-score is 1.20, and her score is 1.2 standard deviations above the mean. This slide shows you Anne's and Rose's scores and their z-scores. And you can see that Anne's score was lower than was Rose's, and to just the same degree her Z-score is lower than is Rosa's Z-score. And here's a definitional term. We sometimes use the term raw score to convey a score expressed in its original units of measure. So for instance, Rosa's raw score is 37. Her Z-score is 1.2. So let's learn some more about Z-scores. You know, we were talking at the end of the prior video about the normal distribution, but I mean, I do want to make it clear that Z-scores can be computed for distributions of any shape. I mean, it goes without saying that we need to have a distribution for a numeric variable, but we don't need to have a normal distribution in order to compute a Z-score. But let's run through some facts about Z-scores. All scores below the mean have negative Z-scores. Those above the mean have positive Z-scores. The Z-score of a case that is precisely at the mean is 0.00. Now, adding or subtracting a constant to all scores does not affect Z-scores. For instance, suppose a professor gave a test and following administration of that test decided that the test was too hard. The professor might then, for instance, add 5 points to each score. So the constant 5 is being added to all scores. If the professor did this, that would not affect students' Z-scores. Each student's Z-score would remain precisely the same. It is also the case that transforming all scores to Z-scores, in other words, carrying out the Z-score formula for each case and calculating each case's Z-scores, and then looking at the distribution of the Z-scores. Well, transforming all scores to Z-scores doesn't affect shape of distribution. Suppose, for instance, that a variable has a strong positive skew. Suppose then that all scores are transformed to Z-scores. The Z-scores will have a strong positive skew, just as did the initial raw scores. Indeed, the shape of the distribution of the Z-scores will be identical to that of the raw scores, that is, to the shape of the scores prior to transformation. Well, let's find out some things that Z-scores can do. Z-scores can help you compare apples and oranges, as the expression goes. So here are Sally's scores on 2 tests, 75% in math, 85% in history. In terms of actual scores, Sally's score is better on the history test. Now, here are the means and standard deviations for Sally's class on the 2 tests. So you can see that the math test was the harder of the 2. The mean was 70% versus 90% for history, and it's actually the case that scores are spread out more on the math test. The standard deviation is 10% versus 5% for the history test. Let's go ahead and compute Sally's Z-score on both tests. So this is going to give us her relative standing compared to her peers, in essence. So here's the math computation. Sally's score minus the mean divided by the standard deviation. Sally's Z-score is 0.50, so she's scoring 1/2 of a standard deviation above the mean in math. Relative to her peers, she's above the mean. How does she do in history? And you can see the calculation. I mean, her Z-score is below the history mean, so we know she's going to have a negative Z-score. her z-score computes to -1. So that even though Sally's raw score is higher in history, relative to her peers, Sally did better in math. Z-scores put all numeric variables on a common measurement metric. By that I mean that when a variable is expressed as a z-score, in other words, when the z-score formula is carried out on each score so that each score is computed to a z-score, and then those z-scores become our new variable. So expressed as z-scores, all variables have a mean of 0 and a standard deviation of 1. This makes comparisons easy. That's why we could look so easily at Sally's relative performance in history and math. So you can think of converting different variables to z-scores as standardizing the different variables. And indeed, another term for z-score is standard score. Z-scores are putting all numeric variables on the same measurement metric. As I expressed a little bit ago, z-scores can be calculated for numeric variables with distributions of any shape. You don't need to have a normal distribution in order to be able to calculate a z-score. So for any numeric variables, z-scores will tell you whether a given score is above or below the mean. For instance, Sally's z-score on history was -0.50. This is a negative z-score, and it's telling us that Sally scored below the mean. And you know, whenever you see a negative z-score, that's conveying to you a score below the mean. That this is not simply the case for normal distributions. And a positive z-score is for all numeric variables, conveying that the case's score is above the mean. For the normal distribution, z-scores convey additional information beyond whether the score is above or below the mean. Recall from the end of the prior video that we were doing all kinds of problems pertaining to percentages for scores precisely 1, 2, and 3 standard deviations above and below the mean. And we were doing those percentage problems for the normal distribution. So indeed, if we have a normal distribution, we can use a table of z-scores, and we can do the very same kind of calculations for z-scores, not just for scores precisely 1, 2, or 3 standard deviations above or below the mean. So here are 4 questions posed. I'll try to read them quickly, and all pertain to a normal distribution. What percentage of cases are between the mean and a z-score of 1.26? What percentage are between the mean and a z-score of -1.26? What percentage have z-scores greater than 1.26? What percentage have z-scores less than -1.26? Appendix A, Table 1, I think, towards the back of your book, is a table of z-scores. And this z-score distribution table lists for many z-scores both the percentage of cases between the mean and the z-score, and then also the percentage of cases that differ from the mean by more than the given z-score. Now notice that each of these columns, this column and this column, and for that matter this column over here too, each of these is listing information for both positive and negative z-scores. And the information is the same on the negative and positive sides of the normal distribution because the normal distribution is symmetric. So our first question probed the percentage of cases located between the mean and a z-score of 1.26. We come down the first row to find 1.26. We come over to the middle column, and here is the percentage, 39.6%. Then the second question from the prior slide asked about cases between the mean and a z-score of minus 0.126. And, this is just the very same question, but on the negative rather than the positive side of the distribution. So we stick at the very same row, and we have the same response, 39.6. Now, the third and the fourth questions from the prior slide were asking about percentages of cases that differed from the mean by more than did given z-scores. And those percentages are in this third column. So what percentage of cases in a normal distribution have z-scores greater than 1.26? And the answer is 10.4%. What percentage of cases have z-scores less than minus 1.26? Again, the answer is 10.4%. While we're looking at the z-score distribution table for the normal distribution, do take a second to see that for each row, the percentages add to 50%. So, for instance, for our top row, 36.4% are between the mean and a z-score of 1.1, and then 13.6% have z-scores greater than 1.1, and 36.4 and 13.6 sum to 50%. These two columns must sum to 50% because in sum, 50% of the cases are greater than the mean. And obviously things would work the very same way in the negative direction. Here's visual representation of the percentages that we've been querying about. So for instance, this line is at a z-score of 1.26. In other words, it's 1.26 standard deviations above the mean. And here is the visual representation of the 10.4% of cases in the normal distribution that have z-scores greater than 1.26. Though I'll reiterate later, let me just take a moment to phrase the same question in two ways so that you very clearly see that these are just different ways to ask this same question. First way to ask the question, what percentage of scores in a normal distribution have z-scores of 1.26 or greater? The answer is 10.4%. Now the very same question phrased a little bit differently. In a normal distribution, what percentage of cases are located 1.26 standard deviations above the mean, or more than this? And the correct response is, again, 10.4%. This is just reiterating that z-scores are always referring to how many standard deviations the case's score is above or below the mean. Well, let's do a problem that involves both sides of the distribution. What percentage of cases in a normal distribution have z-scores between minus 1.26 and 1.26? So we're simply querying here about both sides of the distribution. To get the correct answer, we're going to double the percentage on either side. So we come up with 79.2% of cases are located within, and I'm going to phrase differently, 1.26 standard deviations of the mean. And then the question at the bottom of the slide is asking basically about the tails of the distribution. So it's saying, what percentage of cases have z-scores either lower than minus 1.26 or greater than 1.26? So it's asking us to consider both tails, both directions, and we know that the percentages are 10.4% for each of those areas, so we simply double the 10.4%, and the correct answer is 20.8%. And note that 79.2 and 20.8 sum to 100%. That is to all cases. So this question here is a little different still, in that this question really involves both sides of the distribution. So it's asking you, what percentage of cases in a normal distribution have z-scores greater than minus 0.84? So we locate the z-score of 0.84, and you know that this refers also to minus 0.84. And 30% of cases are between the mean and that z-score. Now then, you know by definition that 50% of cases are above the mean. Another way to say this is 50% of z-scores are above the mean. So to solve this problem, we're going to take 30% and add to it 50%, and we'll conclude that 80% of cases in the normal distribution have z-scores greater than minus 0.84. So here's a visual depiction of the calculations we just carried out. Here's our 30% of cases between the mean and 0.84 standard deviations below the mean, and here's our 50% of cases above the mean. And these percentages sum to 80%. So we've done various problems pertaining to percentages for the normal distribution. Let's do a quote trick problem. Scores on a self-esteem scale are negatively skewed. Dan's z-score is minus 0.84. What is Dan's percentile rank? Or perhaps I might want to ask, what percentage of cases have z-scores higher than Dan's score? Or say between the mean and Dan's score? Any kind of a question pertaining to a percentage. Well, at least in this class, we cannot solve this problem. You are only going to be able to do percentage problems for the normal distribution. So the correct answer to this problem is cannot be determined. You know, the one thing we can know, this z-score is a negative one, so what we do know is that Dan's z-score is below the mean. Here are two final questions for you, and they're just reiterating again the definition of a z-score. The first question asks, Fred's z-score is 2.22. How many standard deviations is Fred's score above or below the mean? And the correct answer is A, 2.22 standard deviations above the mean. And the second question states, Fred's score is 2.22 standard deviations above the mean. What is Fred's z-score? And the correct answer is that his z-score is 2.22. So z-score and how many standard deviations a score is above or below the mean are the same thing. And I think that concludes Chapter 5.